Polymers like rubber are made of very long molecules, usually tangled up in a configuration that has lots of entropy. We're gonna model this as a rubber band, considering a chain of n links. Each link has a length of small l.
Part A and B would both be just 2 joules, right?
And each link has two possible states. Each link can either point to the right or it can point to the left. And we are told that the total length of the rubber band is the net displacement from the beginning of the first link to the end of the last link. So part A, we need to find the entropy of the system in terms of N and NR. NR meaning, as the question said, the number of links pointing to the right. Okay, so we could model this as exactly as a coin having heads and tails. Here we have kings pointing to the right and kings pointing to the left. And the total number of links, I'll start with part A. I've lined these up next to each other so we could see the question and the question text and its parts right next to each other. Okay, so for part A, we know that n has to equal the nr's plus, let's call the ones pointing to the left nl's. Okay, so I'm trying to find an expression of the entropy only in terms of nr and n, so I need to eliminate nl. So nl will be n minus nr. Okay, and we are looking again, we're gonna model the system as that of coins, and we are looking at how many ways we can arrange the links in the chain. So we're gonna find the multiplicity to be, we're gonna use the same formula, except here total is n factorial over n right and left factorials, and we're gonna replace n left by n minus nr. Okay, and as we know, the entropy is just k ln the multiplicity. This is the multiplicity, so entropy is k ln this, and so this will be k ln n factorial over nr n minus nr. Okay, and we're gonna expand this log, and in the process of doing so, we will use Stirling's approximation in order to simplify this. Stirling's approximation says that ln of n factorial for very large n's can be approximated as n ln n minus n. So if I do that, I will get k ln n factorial minus ln nr minus ln n minus nr factorial. And now I will use Stirling's approximation on each one of these three terms, once on n, once on nr, and lastly on n minus nr. So the entropy will become k So the first one will get me exactly what I wrote in red, an ln minus n minus an r ln n n r plus, we'll distribute the minus sign, an r minus, let me use some parentheses here, n minus n r ln n minus n r minus n plus n r. Okay, let's expand this through and see what we get. So I'm going to distribute the ln on the parentheses. Plus first term stays as is. Oh, the signs here switch because I have a bracket. I have another bracket. This is plus minus. So these two guys will go away. These two guys will go away. And we have minus nr ln nr minus. Since there's nothing I could do with these two, I'm gonna factor back out the ln and minus nr. So I will get minus n minus nr ln this is the entropy. This is as far as we can go with this. Okay, for part B it says write down a formula for L in terms of N and NR. Well, as was already said in the body of the question, the total length of L is the net displacement, right, times the length of each link. So for part B, the net displacement will just be the difference between the two sided links, absolute value, because you could have more right or more left, doesn't matter, the difference between them, because if you have 5 going right and 3 going left, the net difference would be 2 either way, regardless of which one of them is the 5 and which one is the 3. Okay, so we wouldn't be repeating, times the length of each link, and this will give us L. Now we will replace an L with NR n minus nr, so this becomes a plus nr times L, and so we will get L to equal 2nr minus n times the length. Okay, part C, it says for a one-dimensional system such as this, the length L is analogous to the volume V of a three-dimensional system. Pressure P is replaced by tension force F. Take F to be positive when the rubber band is pulling inwards. Write down and explain the appropriate thermodynamic identity for the system. Okay, so the thermodynamic identity is du is equal to TdS. There's no chemical potential involved here because we are keeping the number of links the same, so we're not changing the number of molecules, so to speak. So I could use the short version of the thermodynamic identity, TdS minus PdV. Now he says that if the band is pulling inwards, F is greater than 0, so the work is done on the band when the change in length is positive. And so in other words, my minus PdV, if we're gonna treat the force as the pressure here, will just be F dl. Okay, and so we could replace that with F dl. So now the thermodynamic identity becomes TdS, ds being the change in entropy, plus F dl. Okay, for part D, let's see. It says using the thermodynamic identity that we had, you can now express the tension force in terms of the partial derivative of the entropy, and from this expression find out the tension force in terms of LT and NL. Okay, well, assuming that when we stretch the band, the energy remains unchanged. Okay, so we will use the fact that du is equal 0. There's no change in the internal energy of the band, and therefore if I do that, I will get, plug it in the thermodynamic identity, I will get F dl equal minus T ds. So F will equal minus T ds over dl. I could take this to be a partial derivative now, holding the internal energy constant. The internal energy is not changing, and we know from part A, we've already said that L is equal to 2nr minus n times L. Okay, and so what I need to do now in order to figure out I need to find the differential dl. so I could differentiate this expression with respect. Now I know that n remains fixed, and so this will just give me 2L times the partial derivative of nr with respect to L. In other words, what I'm trying to do here is, because I do not have a direct relationship between S and L as of now, I'm trying to use the chain rule in order to say that my change of entropy with respect to the length of the rubber is just equal to ds over dnr times dnr over dl. Okay, and if I plug this in there, if I plug the relationship into my chain rule, I will get for nr. So from here I could solve for my nr, which will be L over L minus L over 2L minus n over 2, or plus n over 2. This is my nr. Okay, so if I plug this in, I will get my f to be, okay, so now that I found a relationship between nr and L, capital L, I could differentiate, I could find the partial derivative of nr with respect to L. I guess what I'm trying to do here, just so we could make sense of this, notice that in part A, my entropy is a function of n and nr. And so what I'm trying to do, I'm trying to end up with a result that has only the partial derivative of ds over dnr without any other partial derivative components left out, so that I could actually go and differentiate the expression from part A with respect to nr, and I could take care of the second partial derivative dnr over dl right here at this moment from the relationship that I derived in part B between the length of the rope and nr. So with that in mind, let's here find out the dl dnr over dl from this expression here. So dnr over dl, partial derivative of this with respect to nl, will be 1 over 2l. And now I could replace this guy with 1 over 2l. So my force becomes minus t ds over dnr, which I will compute from part A as I explained, times 1 over 2l. Okay, let's box this. So this is expressed as a partial derivative of entropy with respect to nr, and now I will continue to answer the second part of the question, that says compute the tension in terms of L, T, N, and L. So I'll go ahead and differentiate S with respect to NR. So let me copy this here. So I will have my F minus T over 2L D over D and R of the entire entropy, which I will put here, which is this green expression. I'm just gonna try to copy it and paste it so I don't have to rewrite it. Copy. Okay, let me fix this a bit. I'll remove this K over here, and then I'm taking the partial derivative of this with respect to NR. That's my S with the K. So F okay, so we get, so there's some so this is gonna be 0. There's no NR here. We're gonna do product rule on this, so this is minus NR times 1 over NR plus ln NR. Well, there's a minus, so let's just make it minus. Okay, and then here the first term does not contribute. It's just the second term, which is plus NR ln n minus NR. Again, a product rule on this, so we will get plus ln n minus NR plus NR times 1 over n minus NR times the chain rule, which is minus 1 because it's minus NR inside the ln, and this becomes minus TK over 2L these guys cross, minus 1 minus ln NR plus ln n minus NR minus NR. Oops, wait, I think we've made a mistake here. Sorry, I thought this was addition. Wait, this actually distributes, so we have to take the product rule on the whole thing, not just this. Never mind, I missed the times. Okay, let me repeat this step here. So we will get minus 1, so this is 1 times ln n minus NR minus, first as is, times 1 over n minus NR times minus 1, which would make this a plus. Okay, so this here becomes a 1 and it would cancel with the -1 at the beginning, so these two go away and I'm left with ln n minus mr. Okay, not bad. And so after all is said and done, we will get f to be minus tk over 2l ln. This is just the difference of two logarithms, so it's n minus nr over nr. Now I did get the derivative, I did get an expression of f. However, the question I think asks to only have LT, N and L, so I need to eliminate NR from my expression, and that I will find from, I already did actually, it's here. NR is L over 2L plus N over 2, so I will take this and I will plug it there for NR. Actually, let me simplify this here a bit. Okay, this is just ln n over nr minus 1. Okay, and I know that my nr from up there is equal to where did it go? 1/2 L over L plus N. So plugging this in, I just factored the half out, I will get okay, common denominators, algebra stuff. You will get n minus L, maybe I should just distribute this back so I can collect these n's, minus half n over 1/2 L over L plus n, and n minus half n is half n, so I could cross out the halves. There's gonna be a half here, there's a half here, and there's a half when I sum up the n's.
1 over 300.
And so f would equal to minus tk over 2l ln n minus L over L over L plus N. Oops, 1 second here, I forgot an L over L here. Okay, when I cancelled the half. Okay, so if I multiply up and down by that, I would get minus tk over 2l ln ln minus L over ln plus L. second minus L over 2. Yeah. Okay, good. So this here is my F. My force as a function of L, N, and capital L. Part E says, show that when the length of the rod is a lot less than the number of links times the number of links times the length of each link. In other words, the total L's summing up all the links is a lot larger. The length of all the links is a lot larger than the actual length of the rubber band, as taken to be the absolute value as we calculated it in part A. We need to show that the tension force is directly proportional to L, which is Hooke's law. Okay, so let's do the approximation for part E. Taking L to be a lot less than an L. In other words, L over NL is a lot less than 1, dividing both sides by NL. Okay, so if I go back to the force, so F, I will rewrite it and do a Taylor series approximation on the Ln to try to answer to get to the desired result. So this is, so I'm trying to get L over NL so I could make the approximation. So if I could divide by NL throughout, so I would get 1 up or L over NL divided by 1 plus L over NL, and this would be minus TK over 2L Ln 1 minus L over NL minus Ln 1 plus L over NL. Okay, since L over NL is a lot less than 1, I could do a Taylor series expansion on each one of these. So let me start with the first one. So Ln 1 minus L over NL, right? This is if I can expand this in Taylor series. Well, let's we've already done that before, but I'm gonna try to summarize here. And generally speaking, if I have L of n of 1 plus x, where x is a lot less than 1, okay, I could expand this in Taylor series. So so let's see what the expansion would be like. We know that this is gonna be, if I call this f of x, then f of x would be f of 0 plus f prime of 0 divided by 1 factorial times x plus f double prime of 0 over 2 factorial times x squared plus higher order terms. Okay, so f prime here would be 1 over 1 plus x, and f prime, and by the way, f of 0 would be 1. F prime of 0 would be 1, 1 over 1. And if I go up to second order Taylor, minus 1 over 1 plus x all squared, and f double prime of 0 would be 1 minus 1. Plugging all this into Taylor, I will get ln 1 plus x to be f of 0, which is 1, plus 1 over 1 factorial, which is 1, plus 1 over x, minus 1 over 2 well, here with x is actually yeah, x squared plus higher order terms. Okay, so that means what I'm trying to say, if I could use this on my terms, I would conclude that ln, so my x on the first one is minus L over NL, and on the second one it's L over NL. So if I do the first one first, L over NL, since L over NL is a lot less than 1, so that would be my x minus L over NL. This would be, oh, I forgot the x here. This would be 1 minus L over NL, plus higher order terms, which I will ignore, and then likewise the L over NL will be 1 plus L over NL, plus higher order terms. Okay, so plugging these back into F here, my F now is minus TK over 2L, and we've got 1 minus L over NL minus the second one, so minus 1 minus L over NL. And clearly these guys go away, and I'm left with F equal minus TK over 2L, and these two terms add up, minus 2L over NL and second. And this L goes away with this L, and so I'm left with F equal 2TK. Oh, actually the 2 goes with the 2 as well. TK over N L. Right, did I forget any terms here? Oh, I know where I messed up. Apologize about that. This is small L here. This is small L. This is, I'm just gonna change this to small L, but everything else remains valid. So this will be oh yeah, because I mean the L would cancel out, it wouldn't make any sense. This is small l back here, small l. Okay, and so these two don't cancel. That's what I thought. It didn't make sense to me that this force would be independent of the number of the length of each link. Okay, so that should fix it. Okay, and so we get tk, or the length of the rubber for that matter. So this is over nl squared. So this is my force fixed. And so yeah, this is exactly what the question is saying. The tension force is directly proportional to L, because you know that's what we're trying to prove. That's why it didn't make sense to me that capital L would cancel out. So so yeah, it's proportional to L, so hence proved. L is in the numerator, and we know that Hooke's law is kx, F equal kx. So x would so Hooke's law first, let me circle this. Hooke's law is satisfied. That says F equal kx or minus kx, depending whether we're talking about the force on the spring or by the spring. So x here is L, and this guy here is the spring constant. This is our ks. Exactly what Hooke's law demands. Okay, let's go through the last couple parts. It says, discuss the dependence of the tension force on the temperature. If you increase the temperature of a rubber band, does it tend to expand or contract? Does this behavior make sense? Okay, well, clearly from our equation, the force is directly proportional to the temperature. So if the temperature increases, okay, the force would definitely increase. Okay, now does this make sense? Yeah, of course. The temperature is also, notice that T and L are in the numerator here, so if one goes up, the other goes down, so they're inversely proportional. The length of the rubber band is inversely proportional to the temperature, and so the rubber band contracts when the temperature increases. Okay, so this makes perfect sense, right? As you increase the temperature, there's more states, there's more the number of links would be much more random, and therefore the randomness increases as far as the links are oriented, and as a result we'd have a contraction, a much larger contraction at higher temperatures than at lower temperatures. So yes, makes sense. And the last part, oh, and one more thing also, as the temperature increases, right, the entropy would also increase, right? Meaning that the number of links that are pointing to the right would have to approach half the number of links, because we've learned that that's the maximum number of probabilistic macro states of the system. That's where the graph peaks, when half of them point right, half of them point left, and in that case L will get smaller as this happens. So there's going to be contraction. Okay, and for part G, the last one, it says, suppose that you hold a relaxed rubber band in both hands and suddenly stretch it. Would you expect the temperature to increase or decrease? Explain, test your prediction. Okay, yeah, you know, I would tend to think that if you stretch the rubber band quickly, then there's going to be a quick increase in the length of the rubber band, and what that means, there's going to be so on top of the total entropy that we've calculated on part A, there's going to be an additional entropy that has to do with the molecules vibrating, which contribute to more vibrational energy, right? So, and this entropy will depend on that increase in internal energy of the rubber band. So then we're gonna have, let me try to write this down briefly. So for part G, if you stretch quickly, right, L will go up, but you also have vibrational energy of the molecules, which will increase the internal energy of the molecules, right? There's going to be an increase due to that vibrational energy in the internal energy of the rubber band, and and of course, if this goes up, the temperature also has to go up, right? Because of that added entropy as a result of that extra vibration of the molecules, giving rise to additional internal energy inside the rubber band, and the T will increase. And we've learned that the entropy depends highly on U. So if U changes, so does the entropy. And if the entropy changes, we learned that the 1 over T, if you guys remember, I believe it was ds over du, right? When we hold the number of molecules in the volume fixed, right? So as U increases, also does the T, because this ratio ds over d, although we'd have an additional entropy created, however the slope would get shallower, and as a result we would get a higher temperature. I think this is enough discussion on this problem. That does it.